That's why we call it electromagnetism. Okay. Now, if I want to create electricity, there's something that lets me do that. Electrons moving around in wires. What do we call that? An electron charge flowing divided by time. Charge over time. Is somebody said it? Current, right? And current creates magnetism. Right? We can see this in a couple different ways. Creates magnetic forces. F equals Q times V times B times sine of theta. Right? That's charges moving at some velocity. We can also think about this a different way. We can also think about this as current. Force is I times L times B times sine of theta. Both of these are moving charges, right? A charge Q moving at a velocity V inside of a magnetic field, or a charge per unit time flowing down a wire of length L times B. Same things, right? Just two different ways of thinking about it. Both creating magnetic forces. Something else that happens with magnetic forces is EMF. EMF stands for electromotive force. And the electromotive force is all about one thing. It's all about flux. What's the symbol for flux? Nobody knows the Greek alphabet, so you're all, let me write in the air what it looks like. I think somebody said it, phi. This is the Greek letter phi. This is electric flux. Electric flux is B times A times cosine of theta. Which means that this is actually a dot product. To remember that, you'd have to go back to like the second week of the fall semester, which is kind of a pain in the butt. So we'll do the abbreviated version here. Phi, you think of as B times A cosine theta. And occasionally we attach on this thing called n hat. I saw some questions about what n hat is. N hat is a normal unit vector. Unit vector means it's 1, so it doesn't change the size of anything. Normal means it's perpendicular. That n hat means we're talking about a vector that's perpendicular to the area that you're talking about. So if I'm talking about flux, let's say I draw a little sheet. So imagine that as like a sheet of paper. So that's what that is. And then I can send a magnetic field through this. I can set up a magnetic field, and I could have a magnetic field that looks something like this. A magnetic field passing through that. Then I could take another sheet, and I could create another situation with some flux. And here I'm going to have 2 magnetic field lines going through this. 2 things to point out. First thing, what direction is n hat? N hat is a normal vector to your surface. So if this is my surface, this sheet of paper, the normal to it is perpendicular. So this would be normal. If I flip it upside down, if I flip it kind of like this, the normal to this would be right side up or down. Okay. So that's what the normal vector means. Now when looking at these, which one of these situations, the one on the left-hand side or the one on the right-hand side, has more magnetic flux? Right side or left side? Which one has more magnetic flux? Left side or right side? 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 Okay. Be confident in your answers, okay? Right? Why the right? It has 2 lines. More lines, more flux. Okay, so this is a greater flux. Bigger flux. Okay, so we have this magnetic flux. And something else that happens with magnetic flux is you induce EMF. So this is Faraday's law and Lenz's law included with it. EMF that's induced is equal to negative n times d phi over dt. So this d phi dt is a change in flux. N represents the number of wire loops that you have making that flux. And then the negative is Lenz's law. So this whole thing is the concept of induction. This is the craziest thing in all of electromagnetism, I think. Okay. And what happens with induction is if you change a current, you change a magnetic field. And this isn't a one-way street. If I change a current, magnetic field changes. If I change a magnetic field, then the current changes. These each change each other. Electromagnetism. Think of current as electricity, magnetic field as magnetism. Electricity changes magnetism, magnetism changes electricity. But nature hates change. Nature resists anything changing. Whenever you start creating or making a change in something, nature is going to create a current or a magnetic field that will resist that change. What does that mean? What does that look like? Let's do some examples, some complete conceptual examples. So if I have a starting situation where I have two magnetic fields. Here's what I have initially. Two magnetic fields. What direction are those magnetic fields going? They're coming out of the board, coming at you. What is that? In unit vector form? K hat. So these are both coming in the K hat. And then in the ending situation, I set up this system, however I do it, so that I actually have three magnetic fields. Does nature like having three magnetic fields coming at me? Nope, it doesn't want that to happen. It resists this change. So what's going to be induced? It's going to induce a field that resists it. It wants to go back to the way things were. Induction is basically a boomer. Make everything back to the way it was. I started off with two magnetic fields, both coming out. I end up with three magnetic fields coming out. Induction wants to cancel out whatever changed. So what is induction going to do? Say louder. Make a magnetic field, and that magnetic field that it makes is going to cancel it out. So it's going to induce a magnetic field that goes into the board so that it cancels out this magnetic field that's coming out. It's resisting that change. Let's do another example. Let's say I have three magnetic fields all going up. And then I end up with two magnetic fields. What's going to be induced? I'm going to create another magnetic field. What direction is it going to go? Up, down, left, right, in, or out? We're going to have an induced field going up. Started off with three. At the end, I got two. Induction is wants to go back to three. So it's going to create a magnetic field going up so that it gets back to three. Okay. Let's do another one. Ooh, this one's tricky. I'm going to have two fields going to the right and one field going to the left. And then I'm going to set it up so that I have one field going to the right and one field going to the left. What's going to be induced? Another one going to the right. Okay, riddle me this. If I create a magnetic field going into the board and another one that's going up, and And in the end situation, I have a magnetic field that's going into the board and a magnetic field that's going out of the board. What happens now? I hear mumbling. I'd make one going up. As well as in. Can you do that? Can I induce two magnetic fields? Sure, apparently. I had one going in and one going up. I end up with one going in and one coming out. So what do I need? I need to get back to this. So to get back to this, I have to create a magnetic field that's going up. I do that. But then I also need to cancel out that one that's coming out. So I create one that's going in. So that cancels out the one going out. I create this one so that I have one going up. And if I add these two together, I end up back where I started. Yes? Which one's first and which one's second? No. Okay. So what I've drawn here, this is all induced magnetic fields. That's not always what you need to know. You don't always need to know the direction of the induced magnetic field. Sometimes you need to know the direction of the current that will induce this magnetic field. Because magnetic fields are created by currents. And to know what current is induced, you need to use the right-hand rule. And there are a few different right-hand rules. Let's talk about the first right-hand rule. This will work when you're trying to find working with V, B, and F, or if you're working with I, B, and F. So let's say I have V going this way, B going down. What direction is the force going? So I take my right hand, and I recommend actually doing this, picking up your sheet of paper and holding it up while you're doing this. This helps me. Put my fingers in the direction of V. I bend them in the direction of B. My thumb is pointing into the page, so my force is going into the page. Figuring out these right-hand rules, we have to be really good at these. So let's say I've got a V going in and a B going to the right. So if my V is going in, I rotate my hand around so I can bend my fingers going in the direction of B. My thumb is going down. That will give me my force going down. That is the first right-hand rule. We've done that a ton. Second right-hand rule. This is typically used in induction. So this is the big one for induction cases. You're given an I, and you want to know what direction B is going. So let's say I have a wire with a current that's going down. This is, again, I'm given I, a direction for I want to know where B is going. So for this one, I take my thumb and I point in the direction that I is, and I take my fingers and I kind of point them to the part of the wire where I want to know the magnetic field. And then the bend gives me the direction of the magnetic field. B is for bend. So if I want to know what the magnetic field direction is on the left side of this wire, I need to take my thumb and point it down. I need to take my fingers, and I would need to rotate my hand around so that my fingers are pointing to this left side of the wire. And then when I bend them, what direction are my fingers going? Into the board. So on that side, my magnetic field is going in. Changes for the opposite side. Thumb going down. Take my fingers, point them over towards this direction, towards this side of the wire. When I bend them, what direction are they going? They're coming out. So it's dependent on what side of the wire you're on. That is the second right-hand rule. Let's do this from a different perspective. Instead of looking at a wire from the side, let's assume that we're looking at a wire coming out towards us. So this would be a wire that looks like this. Current is coming out towards me. Okay, here's my thumb pointing in the direction it's coming. If I want to know the magnetic field right above the wire, thumb coming out, fingers pointing up towards the direction where I'm interested in. Bend my fingers. What direction are they going?
Negative I.
Negative I, to the left. We have multiple regions that we need to do this for. I've got my eye. I want to know the field over here. Point my fingers over here. I bend them. They're going down. B is going down. In this case, B is a concentric circle, we will see. If I'm underneath the wire, if I'm down here, take my thumb, point it out, fingers pointing down, bend them, we're going that way. I'm going to predict that. Let's see if that's right. Thumb coming out, fingers point them to the place where I want to know the field, bend them, fingers going up. If I were to wrap this all around, I would see that this is actually tracing out a concentric circle at any point. So the magnetic field goes concentric. Okay? So let's do a full example of the concept behind this. And this will help with the in-class problem that you have. Let's say I have a current flowing in a wire in this direction. And then I have a wire loop that's underneath it. Now let's say that I take some current. Well, first, let's establish what magnetic field exists that this wire loop is sitting inside of because of this current. So what direction is the magnetic field that this thing is sitting inside of going? So I take my thumb, point in the direction of the current, and then I need a step ladder so that I can get high enough. Maybe. Yeah. Okay, there's my thumb. I want to know what's going on below this wire, because that's where my wire loop is. So I put my fingers below. And when I bend them, what direction are my fingers going? Into the board. So this wire creates a magnetic field that this thing is sitting inside of that's going into the board. Now let's say that I change this current. I'm going to increase this current. So instead of having one current line, maybe I create a little bit extra current so that there's more current going in. So what is the direction that increasing current is going to cause for the magnetic field? Is it going to create more magnetic fields coming out or more magnetic fields going in? It's going to create another line going in. Okay? This wire loop is not happy about that. Nature does not like change. So some current is going to be induced inside of this loop that's going to resist this. It doesn't want this extra blue line. So it's going to try to get rid of it. So what direction is the induced magnetic field going to go? Out. So we're going to create a magnetic field that's coming out. Okay, so that's B. That B is created by current that's going to start moving inside of this wire. I need to figure out what direction that current's going. That current could be going clockwise through this, or it could be going counterclockwise. I can pick any point on this wire to figure out the answer of the direction for the induced current. Which piece of the wire do you want to use? Do you want to use top, bottom, left, or right side?
Top.
Top. Okay, I'm going to use this top wire. My current could be going to the right, or it could be going to the left. Induced current. Take a guess. What do you think? Is it going to the right or going to the left? You're going to guess to the left? Okay. So let's say that this current is going to the left. Let's see if that works. So I've color-coded this so that red is induction. Red is the stuff that's induced. So I want that direction of that induced current to to give me a magnetic field that's coming out of the board. Let's see if that works. I take my thumb, I point in the direction the current's going. I want to know what the magnetic field is down here. So I point my fingers down, and when I bend them, where are they going? Out of the board. Is that what I want? Yes. So did I guess correctly? Yes. So I'm good. What happens if I didn't guess correctly? Then just flip the direction. Does this work no matter where you go? So if this current is going to the left here, what direction is it going to be going in this part of the wire? It's going to be going down. Let's see if it works. Anybody want to bet me that it won't work? I got to pay for an engagement ring and a vacation to Disney World, so I will bet you that this works. Okay, let's see. So I take my thumb, point it down. I want to know the magnetic field over here. So I point my fingers over in that direction. And when I bend them, coming out. It works. Will it work down here?
Yes.
Yeah. So what direction would it be going down here?
Right.
Goes to the right. Let's see. Take my thumb, point in that direction. I want to know up above the wire. Point my fingers above, bend my fingers up. They're coming out. It works. And take my word for it that it will work on this end too. So what direction is this current flowing? Is this clockwise or counterclockwise? This would be counterclockwise for the induced current. Okay. And if I wanted to know what the size of this magnetic field was, how could I figure out the size of a magnetic field created by a current in a long straight wire? What's the general equation for magnetic field due to a long straight wire?
Mu I over 2 pi r.
Mu naught I over 2 times pi times r. All of this here on this little screen, this is everything you need to be able to do the problem that you have to do in class today. So that is induction. Any questions on induction and magnetic fields?